Hello. So we're going to do our second example of a hypothesis test here. So the situation for this one is as follows. It is known that blood pressure has it's a mean of 120 millimeters of mercury. I think that's the unit of pressure they use there. So we're saying that the population of humans has this average blood pressure. But a researcher believes that has reason to believe that the blood pressure might be higher in Honolulu. So this researcher or a team of researchers samples 100 people in Honolulu and finds that the sample mean blood pressure in this group is 130.1 millimeters of mercury, and that the standard deviation of the sample is 21.21 millimeters of mercury. And so the question is this a statistically significant finding? In other words, is there reason to suspect that the average blood pressure in Honolulu is actually higher than the rest of the population? And we're asked to test with a 1% level of significance. So I'll note that alpha is 0.01. We'll use that at the end. And as usual, we want to write down our null hypothesis and our alternative hypothesis. Okay. So the null hypothesis, remember, is the status quo, that there is nothing out of the ordinary happening here. In other words, that the mean in Honolulu is no different than anywhere else, that we just happen to get a group of 100 people who had a higher mean blood pressure. And so our alternative hypothesis is that we suspect it is actually higher, right? That we found this sample with a higher average blood pressure, and so we think that perhaps there is something different in the population in Honolulu than everywhere else. Okay, so there's our null and alternative hypothesis. So we now need to decide what type of test we're going to run. In this case, we're testing a population mean again, but we don't know the standard deviation for the population. Instead, we have it for the sample. Okay, so that's the sample standard deviation. And so the test statistic is going to be a t-score, and our formula is t is equal to the sample mean minus the population mean. Again, this is the population mean, assuming H0 is true. During the entirety of our test, until the very end when we make a conclusion, we will assume that this is actually the case. The mean is 120 millimeters of mercury. So I've got x bar minus the mean over the standard deviation of the sample divided by the square root of the sample size. So in this case, that is 130.1 minus 120 over 21.21 divided by the square root of 100. And I found this to be 4.762. Okay, so there is my t-score, my test statistic. Now, we're going to do this one a little bit differently than the last one, and I'll try to explain it. Either way is fine, but I want you to see both methods. So let me do a quick sketch here. This is going to be my student's t distribution. Okay, it looks very much like a normal curve, right? And t-score in the middle of 0. My 4.762 is a t-score somewhere over here. All right, so I'm just going to put it there. And the probability of t being greater than 4.762 is my p-value. Okay. Instead of computing that, though, I'm going to find a t-score related to alpha. And what I'm going to do is the following. I'm going to look for a t-score that has 0.01 area above it. Okay, I don't want to messy this drawing up too much, so let me just kind of do a second smaller sketch up here. The same curve, there's some t-score, I'll just use a little star for now, that if you computed the area above it, you'd have 0.01. Okay, so I'm going to find that t-score, and then I'll explain how we're going to use it. So I'm not going to go through, I don't have a table printed out, I have one on a screen here, but you guys have seen the tables. So I'm looking for a t-score that has 0.01 in one tail, right? And I'm looking for, on the table for 99 degrees of freedom, because n is equal to 100 and our degrees of freedom is 1 less than n. Although the table I'm using doesn't have 99, it just has 100, and it's going to be close enough. The numbers change very little once you get very high values of n. And we'll see that it's not going to matter because we're going to have quite a big big difference here. So if you look through the table, what we find is that a t-score of 2.364. So this t-score, if you compute the probability that t is greater than 2.364, you get 0.01. So that's just read from the table. Okay. Notice this t-value is way under the one we just computed. So it's somewhere over here. 2.364, right? And what this statement is saying is that if I take all the area above this t-value, all this area is equal to 0.01. In other words, the probability is 0.01. Well, what does that mean? That means the area here, right, our value, which is less than this total area, has to be less than 0.01. Okay. I don't know what the value is, I just know that it's less than 0.01 from this picture. Okay? So this is our p-value, this is our alpha, and our p-value is less than alpha. Okay? So once again, we reject the null hypothesis with a 1% level of significance. Okay, so that's the other kind of this is the kind of a test we do when we're testing a population mean, but we don't know the population standard deviation. Okay. I also want to note, I mentioned that I was using an approximation since we wanted 99 degrees of freedom, but the table I was using only had 100. I didn't worry about it because these values are so far different from each other, and that one little degree of freedom isn't going to change this number very much. If they were close to each other, I would have had to go to a better table or a calculator. But because this is nearly twice as big, or more than twice as big as this one, I'm not concerned at all that small a bit of approximation here will affect the conclusion here. Okay.